Bismillah ar-Rahman ar-Rahim. We have a polynomial from R to R satisfying the following inequality. F of x minus its first derivative minus its second derivative plus its third derivative is non-negative for every x in the set of real numbers. We want to prove that the polynomial is non-negative. The key to solving this problem is the following lemma. If we have a polynomial g and g of x plus alpha g prime of x is non-negative for every x in R, then g of x is non-negative. I will prove this result or this lemma first, and then we will get back to our function f of x. Let g of x be a polynomial of degree n, and for some alpha in R, so alpha is just a real number, a constant, g of x plus alpha g prime of x is non-negative. If this is true, we want to show that g of x itself is greater than or equal to 0. Note that if there is a polynomial satisfying this inequality, then its degree cannot be odd. If the degree of g of x is odd, then it tends to minus infinity as x tends to infinity or to minus infinity, and this inequality cannot be true. Also, this inequality cannot be true if the degree is even, but the leading coefficient is less than 0. In this case, g of x will tend to minus infinity as x tends to plus or minus infinity. If there is a polynomial satisfying this inequality, then n is even and the leading coefficient is positive. Suppose that g of x attains its minimum at x bar. At x bar, the first derivative of g is equal to 0. Let's assume that g of x bar is negative. Take this left-hand side and replace x by x bar. We have g of x bar plus alpha, which is this real constant, and then g prime of x bar. G prime of x bar is equal to 0, so this is equal to g of x bar. And if polynomial g satisfies this inequality for every x, then this must be greater than or equal to 0. It cannot be less than 0. Our conclusion, given alpha in R and an nth degree polynomial g of x such that g of x plus alpha g prime of x is non-negative, then g of x is non-negative. Our problem looks a bit different. We have a polynomial and it satisfies this condition, which involves the first, second, and third derivatives. The first step is to set alpha equal to 1 and take g of x as f of x minus 2 f prime of x plus f double prime of x. If this is function g, what is the function g of x plus alpha g prime of x? This is f minus 2 f prime plus f double prime, that's g. Alpha is equal to 1, then we need to differentiate. F becomes f prime, minus 2 f prime becomes minus 2 f double prime, and f double prime becomes the third derivative. If we simplify, we have f minus 2 f prime plus f prime, that's minus f prime, plus f double prime minus 2 f double prime, that's minus f double prime, and then we have the third derivative. This is exactly the left-hand side of the given inequality. It is given that this is non-negative. If we choose function g to be defined in this way in terms of function f, then g of x plus the real number 1 times g prime of x is non-negative. This is given. By our lemma, the conclusion is that g of x itself is non-negative. F of x minus 2 f prime of x plus f double prime of x is non-negative. Let's now define g of x to be f minus f prime. G of x plus alpha g prime of x, when alpha is minus 1, this is g minus g prime. This is f minus f prime minus the derivative of this is f prime and then plus f double prime. This is f of x minus 2 f prime of x plus f double prime of x. This is g plus alpha g prime. Now with alpha equal to minus 1, alpha can be any real number, and g set equal to f minus f prime. From the previous step, we have this function proven to be non-negative. By our lemma, g of x must be non-negative. F minus f prime is greater than or equal to 0. The last step is to take g equal to f. G plus alpha g prime with alpha chosen to be minus 1, this is equal to g minus g prime, which is equal to f minus f prime. From the previous step, f minus f prime is non-negative, and by our lemma, it must be the case that g itself is non-negative, and here g is f, so f of x is greater than or equal to 0 for every x in the set of real numbers.